Welcome to this instructional video to replace Friday's class. So, we're talking about in Chapter 7, acids and bases. So let's do some definitions. There's several definitions of these two things. The first definition is called the Arrhenius definition. And the Arrhenius definition of an acid is produces hydrogen ions in water. Now remember, let's go down here and do another definition. H plus is a hydrogen atom that's lost its electron, so it is an H plus. And so we call it hydrogen ion, or it really is just a proton. That's the only thing that's left. It doesn't have a neutron, it doesn't have an electron. It literally has one proton, and so we call H plus a proton. So we may use that term instead of hydrogen ion. So an acid, according to Arrhenius, is something that produces a hydrogen ion in water. Arrhenius also says that a base will produce, or bases, a base will produce hydroxide ion. You remember that? That's one of the polyatomics you have to know in water. So, that's the definition of a base. It produces a hydroxide ion in water. Well, Brownstead-Lowry comes along and says, well, those are good definitions, but here's another way to think about it. An acid is a hydrogen ion donor. It will donate a hydrogen ion to something else. And they said that a base is a hydrogen ion acceptor. Something that will accept the hydrogen ion. And some other definitions or characterizations is that acids are typically sour or bitter. And bases are typically slippery. Think of soap. Soap has base in it, and it is kind of slippery. And think of citrus fruits like lemons are very sour or bitter because they have a lot of acid in them. Alright, so there's some definitions. Let's just move along here. So table 7.1 is one that I am going to ask you to know. These are common acids and bases, so I think you need to know what these are and what they do. And so we have hydroiodic acid, hydrobromic acid, hydrochloric acid or muriatic acid, sulfuric acid, nitric acid. That's just a few common ones. And then bases are sodium hydroxide, potassium hydroxide, and ammonia. I will make special note of the nitric acid. It says it's used to make fertilizers and explosives and dyes. Well, nitric acid can be used to make ammonium nitrate. And it turns out that this can be a fertilizer, but it also is highly explosive. And you can Google Oklahoma City bombing in the early 90s, where a federal building was pretty much blown to bits by ammonium nitrate. Alright, again, I just want you to know these acids and what they do, what they're used for. I think it's important to know that. Let's pick a couple of them to talk about. HCl. Why would we call HCl an acid? And it is called an acid up here because it will dissociate. And here's a good word to know. Dissociate means to break apart. And so HCl in water will dissociate into H plus a Cl minus. That's why it's an acid. It produces, and this will be in water, a hydrogen ion. That's one of our definitions of an acid. What about sodium hydroxide? Well, sodium hydroxide is listed as a base, and when you put that in water, it will dissociate, break apart, to produce Na plus OH minus. That's the definition of a base. It produces hydroxide ion in water. What's another one from this table? NH3, ammonia. It will react with, pick up, accept, if you will, a hydrogen ion to make NH4 plus. And so ammonia, NH3, is a base because it accepts a hydrogen ion. And how do we know it accepts? Because the hydrogen ion is on the same side of the yield sign as it is. So this is accepting a hydrogen ion. That makes it a base. Okay. One thing that we're going to be doing, you're going to be doing a lot, is if I give you an acid, can you write its conjugate base? Because that's what acids do. Acids will act as an acid and it will produce a base. And then conversely, if you have a base, it will act as a base and then become an acid, because that's how this acid-base chemistry works. So, for example, I've given you under here conjugate. I want you to draw a box around, or brackets around, the conjugate bases for given acids. Well, HBr is an acid because it has a hydrogen that can be donated as a H+. And if you put it in water, it will yield H+ plus Br minus. Now, how do I know that it produces Br minus? Well, if you have something that's HBr and not charged, and it kicks out, donates, loses a H+, then what's left over has to have a negative charge. So this right here is the conjugate base of HBr. Alright, CH3COOH. What we know is it can kick out a H+, and then what's left over? Well, something that has a negative charge. So what's left over? CH3COO, and it's going to be minus. How do I know that's minus? Because something that had no charge, CH3COOH, kicked out a H+, and so what's left over has to have a negative charge. We have to have charge balance across this yield sum. So CH3COO minus is the conjugate base in this case. So these are conjugate bases. Now, why do we call them bases? Because they could pick up a proton and act as a base. So that's why we call them the conjugate base. Well, what if I gave you a base? I'm telling you this is a base, and I want you to draw the conjugate acid. Well, how does this work? You need to add a H+ to it. Bases pick up, accept hydrogen ions, and when that happens, you're going to get HCO3 minus. This just makes sense, because if you have a hydrogen added to HCO3, hey, now you got HCO3. And then 2 minus plus 1 plus leaves you with 1 minus. So this is our old friend, the bicarbonate ion. This is the conjugate acid after accepting 1 proton, or 1 hydrogen ion. Because what we know is that now this can pick up another hydrogen ion. And if it does that, you're now going to get H2CO3. So, if this happens, this would be the conjugate acid of CO3 2- after accepting 2 protons. All right, we'll get the positive charges right here. Okay, so CO3 2-, because it's got 2 negative charges, it can possibly pick up 2 H pluses. And you can draw the intermediary when you have only 1 H plus added. That's HCO3. That's the conjugate acid accepting 1 hydrogen. If it picks up another one, it can be the conjugate acid after accepting 2 protons or 2 hydrogen ions. Now F-, how many H pluses can it pick up? Well, it's probably just going to pick up 1 because it's only got 1 negative charge. There we go. F- plus a hydrogen ion yields HF. And then this would be just called the conjugate acid. And typically this is the way we write this. Hydrogen goes first and fluorine is second. So I can give you a series of acids and bases and ask you to draw the conjugate pairs, right? Or predict the conjugate form once something acts as a base or something acts as an acid. We can also do what we call complete acid-base reactions. That's when you have an acid and a base reacting together. Well, in this scenario, the acid donates a H plus, and the base will pick it up. And you just got to draw what happens after this, after this reaction occurs. So I think you can look at this and look and say, well, this has to be the acid because it's got a hydrogen that it can donate as H plus, and this one can't be the base. The Br- can't be an acid. There's no hydrogen. So this is the base. So when you do this kind of transfer, then HNO3 loses the H plus, so it has to be now NO3 minus. And then Br- picks up a H plus. You now get HBr. This is an acid-base reaction. So now the NO3- is the conjugate base, and the HBr is the conjugate acid. All right, so Chapter 7 is largely about acid-base chemistry. Water acids, water bases, what happens when an acid acts as an acid to produce a conjugate base, and what happens when a base acts as a base to produce a conjugate acid. And so we'll practice this more as we go along, but this gives you an idea of how this can happen. And then you can have acid-base reactions, where something is reactive with something else. One wants to give up a H plus, one wants to accept that H plus. Then you have to draw the products of the reaction after this occurs. All right. Well, to finish out this part of the notes, we have to talk about different types of reactions that are said to be reversible reactions. And so the reactions, until now, we've been saying a chemical reaction goes from left to right. Reactants yield products. Well, what we know is that many chemical reactions are reversible. They are in what we call equilibrium. In this case, I've given you a generic example. A plus B is in equilibrium with C plus D, and the lowercase a, B, C, and D are coefficients of the balanced reaction. So what we still call on the left A and B as reactants, and then C and D are the products. So we have reactions that can go both ways, and we say they are in equilibrium. One thing that can be done is you can write an equilibrium expression. And an equilibrium expression basically has you define what we call an equilibrium constant. So let's look down here. KEQ, capital K, lowercase eq, is called the equilibrium constant. And so here's our reaction. It's in equilibrium. We know it's in equilibrium. It can go to the left or it can go to the right. Again, we're still going to call these, we're going to call the participants on the left reactants. And this CO2 on the right is going to be the product, just to basically classify the reaction. Okay? Well, let's balance this because we have to have a balanced reaction to be able to write an equilibrium expression. An equilibrium expression really comes down to the products over the reactants. So KEQ is going to equal the concentration of the product, carbon dioxide, and then we are going to raise it to the coefficient. And so you notice I squared this concentration because this is the coefficient in the balanced reaction. That will be divided by the reactant, so the product over the reactant. So this will be the concentration of carbon monoxide squared, again because that's a coefficient of 2, times the concentration of oxygen. Ladies and gentlemen, this is what we call an equilibrium constant. If I gave you the concentrations of the reactants in the product, you could calculate a KEQ. And then the numerical value of the KEQ tells you whether at equilibrium the reactants are favored or the products are favored. And when I say favored, I mean present in larger amounts. So these rules help us do this. To be honest with you, I don't think I'm going to have you calculate a KEQ. I might. I better hold off on that. But probably what we're going to do most of the time is if I give you a KEQ value, you can tell me whether the products or the reactants are favored. Again, look at this table. Look at the rules. If KEQ is greater than 1, then the products are favored when the reaction reaches what we call an equilibrium. All right? So we have a forward reaction. The forward reaction would be left to right. Let me write this up here. The forward is left to right, and the reverse is right to left. So at equilibrium, if KEQ is greater than 1, then the products will be available or there in greater amount. If KEQ is less than 1, then the reactants are favored. So at equilibrium, you have a reaction that's reversible. The KEQ, the value of KEQ, will tell you which is in greater abundance when the reaction equals equilibrium, when the reaction reaches equilibrium. So in this case, KEQ less than 1, you'll have more reactants than products. If KEQ equals 1 exactly, or real close to 1, you have equal amounts of products and reactants. All right, so we have reactions that are reversible. They can be in equilibrium. We can write an equilibrium expression, a mathematical expression that requires a balanced reaction. If you actually calculate the KEQ, it tells you something about the reaction itself. What's going to be favored when the reaction equals equilibrium? There'll be more reactants or there'll be more products. The last thing we want to do in this video is talk about Le Châtelier's principle, and it has to do with reactions in equilibrium. So in Le Châtelier's principle, you have a reaction in equilibrium, and then you push it out of equilibrium, you perturb the equilibrium, you disturb the equilibrium by either adding something or taking something away. So look at this reaction. It's already balanced for us here. And on the left, we would have the reactants. On the right, we would have the products. This is in equilibrium. And you know it's in equilibrium because you've got the arrow going left to right and then one going right to left. So Le Châtelier's principle is useful because it gives us some rules to know how the equilibrium will shift so it can be reestablished. So let's say we're running this reaction here, and then it's reached equilibrium. And now, by the way, this is an exothermic reaction because we have heat. It's a product. This is an exothermic reaction. So what if you have this reaction and you've run it and it's in equilibrium, and you add more oxygen to the reaction mixture? That's what this means. You increase the concentration of oxygen. What will happen to the equilibrium? The equilibrium will shift to the, now think about it. If you have extra oxygen added to the reaction mixture, don't you want to process that oxygen? Get rid of it. So the reaction will shift to the right in order to reestablish equilibrium. So you're adding oxygen, you're going to shift the equilibrium to the right. What if you took away water? What if you were able to remove water from the reaction mixture? What will happen to the equilibrium? If you take away water, you've left a hole, if you will, on the right where the products are. So to reestablish equilibrium, you need to make more water. How do you make more water? You better shift the equilibrium to the right. Notice I added something first. Now on the second thing I've done, I've taken away water. You could add or take, you can add something or you can take something away. Well, what if we added carbon dioxide to this mixture? Well, you're adding a product. You're adding carbon dioxide. How are you going to process that extra carbon dioxide? You better shift that equilibrium to the left. Extra CO2 to basically get the equilibrium back reestablished, you're going to have to shift it to the left. This reaction to the left to process that extra carbon dioxide. All right. So it's a reaction. You can add things, you can take things away. Le Châtelier's principle, which we're going to use moving forward now, will allow us to predict which way an equilibrium will shift based upon adding or removing reactants or products. Now, what about the temperature? Well, you can use the same logic here. This is an exothermic reaction. Heat is a product. So if you increase the temperature of an exothermic reaction, what happens to the equilibrium? Well, you add extra energy, you add extra heat by increasing the temperature. Well, how are you going to process that extra heat, if you will? Well, you better shift the equilibrium to the left. So if you increase the temperature of an exothermic reaction, you shift it to the left. What about decreasing the temperature of an exothermic reaction? That's in equilibrium. If you reduce the temperature of the reaction mixture, the equilibrium will have to shift to respond to you lowering the temperature. Think about this. If you lower the temperature, you take away energy, you take away heat. Well, there's a hole there. How are you going to get that heat back? The equilibrium will have to shift to the right. So if you increase the temperature, if you decrease the temperature of an exothermic reaction, the equilibrium, according to Le Châtelier's principle, will shift to the right. Now, as an exercise, probably later on after spring break, you can think about what would happen when you increase the temperature or decrease the temperature of an endothermic reaction where heat is a reactant. Ladies and gentlemen, this is Friday's class. We had to get this in to move forward after spring break. Have a great spring break, and I will see you soon.